We will deal with as many questions as possible during this session, but if we can't get to yours today, someone from 3D Systems will be in touch to discuss. Next slide. Just a quick agenda, what we're going to go through, and really just explore the technologies and the use cases and the research for lightweighting metal. Next slide. And I'd like to introduce Brian Hodgson, who is a lead expert in our aerospace team based in San Diego, California, and who has been leading much of the research into metal lightweighting for customers. Over to you, Brian.
Good morning, everyone. So yeah, as Rachel said, I lead our applications division for aerospace. Really, my background is in 10 years of really disruptive engineering technologies for aerospace supply chains. And now what we do here at 3D Systems is help companies industrialize and disrupt their own supply chains using additive. So today what we're going to be talking about is metal lightweighting, and that's a very broad term. So specifically, we're going to really be focusing on the use of powder bed fusion, machine, and software to lightweight metal application. So you know, the next slide. First, a little introduction of 3D Systems. Obviously, 3D Systems is uniquely positioned to really discuss this topic and to help industrialize this production. Founded by Chuck Hull, who's the inventor of 3D printing. He's still our Chief Technology Officer and really kind of a guiding hand on the technology side. As you can see, here's a good infographic kind of walking you through all of the different types of technology we have. And so we really have 7 different types of print platforms, the most in the industry, and 4 to 5 different software platform setups. Really, what it does is it helps walk you all the way from reverse engineering, design, through the machine and material, and then even into the post-processing, allowing you to industrialize and adopt 3D printing for even the most established supply chains. All right, so just as we go forward through this, what we're really going to be focusing on today is lightweighting for powder bed fusion applications. But just know that there's no need to try to fit square pegs into round holes here. We really have a broad portfolio of technology, software, materials, and services to walk through this. Next. So to start, little layout of 3D Systems. We're a global organization. We've got locations all around the world. I'm based in San Diego, California, but we have centers of customer innovation for metal in Denver, Colorado, as well as Leuven, Belgium. We have a production CIC being established here in San Diego, and Rock Hill, South Carolina, as our plastics customer innovation center. So really what we really have established here is the ability to have customers interface with our advanced teams globally and be able to adopt the technology and really learn it in concentrated innovation environments. Next. So redefining metal manufacturing by equations. So today we're really going to just hammer in on how we're doing direct powder bed fusion printing from metals. So one theme you're going to hear throughout the entire time is design. Design, design, design. Every single thing you're going to do with powder bed fusion is going to start with design. If you take an object that's designed for traditional manufacturing and then you throw it into a 3D printer, it does not magically get better. Actually, in general, will be more expensive and be less effective. So really a critical component here, and this is why we're really addressing lightweighting. You must change and improve the design and add value to the part really to make it fit for 3D print. And so you do that in multiple ways. You can increase functionality. If it's a fluid flow device, so the picture you see on the screen here is a model heat exchanger. If you're improving internal fluid flow, if you're reducing part weight, or if you're simplifying your supply chain through part count reduction. Really, all of these are good things, but you have to be able to add value to the part before you're going to really make it a cost-effective venture for powder bed fusion. Next. So, since it all starts with design, let's talk about how we design. Traditionally, if you started, I would say, even 2 years or 3 years ago using powder bed fusion, you would have to start with anywhere from 3 to 5 different software platforms. It would be everything from wherever your CAD package design is, walk through to a build setup. something like a Magix or Materialize or additional software. Then you have to walk through the native software of whatever print capability you're using, and then post-processing would be done on a whole separate software. What really is helpful in that world is 3D Expert. And so we actually offer a software here that allows you to kind of shortcut all of those different translations of software and bring it into one. So I'll talk a little bit about 3D Expert software today. Really what we're going to address is how do we lightweight and how do we use this as a tool for developing 3D print components and applications. So I'll talk a little bit about lattice work, conformal cooling, support optimization, build simulation, and then a few of the tools that are built into the process that allow you to really step it up a level in the advanced material application. We're also going to talk a little bit about solid thinking. So they make a software called Inspire for topological optimization. That's obviously a great software for really developing a reduced weight metal application for structural components. If you go to the next slide, we're going to dig into 3D Expert a little bit first. So what is 3D Expert? So as opposed to the past where you would start with your CAD and move through multiple environments, perhaps convert it to an STL or any number of non-parasolid files or meshes, 3D Expert works directly with any CAD package. So it allows you to input your data, whatever your control functions are. Obviously, this is critical in any industrial environment, aerospace, automotive, healthcare. Being able to use the same support function, the same CAD support function that you use internally, and then kind of transition into 3D print space. So that's where 3D Expert pulls the file in. You're in that environment, you're able to position the part, optimize the structure, and then do a full design of the component. And what that means is, as opposed to just having the component sitting on the platform, maybe just angling it, it also allows you to create supports that are then able to pull back out of 3D Expert as a traceable file. It also has, it's a traceable CAD package allowing you to make modifications within that environment. So changes in hole dimension, offsets, last minute adjustments to the part for printing or even just for part modification don't have to be done through multiple software translations. They all get to happen in the same environment. After that build environment is done, it has some advanced software to help you with your scan path. So obviously, think of how to best using scan paths just like your speeds and feeds on a traditional grinder or mill. This really is the nuts and bolts of how you lay out how you're going to melt the metal. And so this software allows you to vary and change really an unending number of times through a method called zoning that allows you to scan different sections, maybe different downface sections, different areas where you can go faster because you're post-machining, or even slow down and have some tighter metal properties for critical non-inspecting areas. Once that's complete and the software has gone onto the machine, we actually have a process for post-machining as well. So in the aerospace or automotive environments, you'll know that this is not a Star Trek replicator. This is not a machine that you throw a part on there and then poof, you're done. You have a finished component you can use for industry. This is another machine and a suite of machines for your manufacturing industry. So with that in mind, any post-process machining of seal surfaces, machining of key features, or tight CNC lathe turning operations, all of these can be built into 3D Expert by adding material and then even producing the G-code path so that we can go directly to a CNC. Next slide. So let's talk about what optimization tools you have. So we know 3D Expert now gives us an end-to-end kind of solution that allows you to start at CAD and finish up with post-machining. But how does it help you lightweight that part? Well, one of the primary functions is lattice. So if anyone on the call here has worked with lattice before, obviously as a parasolid, it is a very, very data-intensive, bulky process. So most, if not all, other CAD packages out there will allow you to make simple lattice structures, but the more you design, the harder it is to manipulate. And traditionally what people will do is fill up a volume with lattice and then begin to boolean sections of the lattice out to meet the form that they're looking for. The problem with that in additive manufacturing is that as you've kind of booleaned away sections of your lattice structure. Depending on where it generated from, you're going to end up with very different hanging support function pieces that may not print well or at all, and then really suboptimal lattice. 3D Expert really fixes that in kind of an innovative way here. It allows you to render and design lattices kind of in a live space that is not clunky and very fast and robust. So this will allow you to take a single cell, design that lattice, and really design it for 3D printing. So up into designing a whole cell lattice that will make sure that it's always a self-supporting lattice without a hanging a hanging piece. So it does this in a kind of a robust history-based way. What it does is it allows you to build a lattice structure, not just to look like lattice, as in some CAD packages, but really to be a lattice designed for 3D printing. We'll talk a little more about that on the next slide here, is kind of how we go about that. The way this is done is the lattice is rendered directly on your screen, but really the calculations and equations for developing this lattice through the component aren't really fully defined until the slice, right? So what you're able to do is see and render your open lattice, play with it, make it fit the exact function that you're looking for without having to deal with millions of faces in a pair of solids. Here's just a few examples of what comes as an open part of the software. We've got some around nearly a dozen different set lattice structures. These are all variable. You can set based on density infill, anything from solid lattice to a stochastic, from gyroids to shorts to just traditional cell lattice. What it also allows you to do is to design your own. So it allows you to take a cell structure, design your own internal lattice, and then propagate that throughout as a fill space, interior or exterior that you're looking for. And then assign that either to either be a whole cell lattice to interface with the sidewalls. So really the concept I want you to walk away with here is that it's not lattice as you're used to in a traditional CAD package. It's lattice that's meant for 3D printing. It's really purpose-built because that's really the only way you're going to build this lattice anyway. A key note on the top left here is some of drain holes. And so obviously, right down the line of being able to print this lattice, if you're going to have an interior cavity filled, that interior cavity, if you're not going to post-center the metal in there, you're going to have to drain it. And so draining material out of key passages is a critical component for lightweighting using lattice. All of this is built into 3D Expert. This allows you to make sure that you know where your powder is going to be when you're done, and helps you kind of design that function as well. Next slide. So finally, now that we've talked about how we want lattice, and we want lattice designed for 3D printing, not just to look good on a computer screen, what do we do with it? How do we use that lattice? And so this is a function built in the 3D Expert that allows you to analyze and optimize. So to date, if you were to build any sort of structure, once you got above 5 inches, 5 by 5 by 5 inches, you've really created millions of pair of solid faces that unless you have a supercomputer or two at your disposal, you're not going to be able to analyze. What we've designed into this feature is an analysis FAA tool specifically for lattice cell structure. It's important to note that obviously you're not going to be using something like a lattice structure for any fatigue-rated items. So anything that's going to be subject to high cycle fatigue, you're not going to be using lattice anyway for its fatigue properties. What you're using lattice for really is to fill space and to add internal structure to a thin wall component. But how do you know what structure you've added, and how do you know what density infill you can get away with? Obviously, the less the better. And what kind of stresses are going to be on that lattice? Is it going to break immediately, or have you made it overly robust? So this is where our lattice-based structural optimization comes in. It allows you to analyze that lattice to say, yes, we've got high stress concentrations, your von Mises stresses are well underneath the yield strength of whatever you're using, titanium, aluminum, and really design an internal or external lattice fill structure that provides a known level of support. So this is critical. Obviously, we could likely spend the entire 35 minutes just on lattice lightweighting, but I wanted to kind of give everyone on the call here a taste of where 3D Systems sees the lightweighting work going, and really we see it as a initially a software setup issue that kind of bleeds into how do you build it with hardware. So, we go to the next slide. Kind of speaks directly to what I was just talking about. So, now we've talked it through how are we designing something for lightweight. Now we've gotten to the printer section. So this is our proactive DMP 320 solution, so DMP for direct metal printing. In the aerospace or automotive industry, anytime you're focusing on something that you need repeatable production, really your powder chemistry is going to be critical. So again, we could likely spend the entire time walking through just the details of powder bed fusion. But one thing I want to hit on with this slide that I need to walk away with here is there's really two types of powder bed fusion systems. Fundamentally, there's the powder bed fusion systems that operate with a vacuum base, and then there's fusion systems that operate just through an inerting purge gas system. Right, so if you have an operation that uses just inerting purge gas and then kind of has a recycling powder system, what it does is it'll spend the first hour or more purging the system with either an argon or a nitrogen, and then every time material is deposited across the powder bed, what you'll see is a spike in oxygen content. So remember, this, as fun as 3D printing is, it really is nothing more than a very advanced welder with a very fine powder. And so, critical step in welding is how much oxygen is at the weld bed. So now, if you're operating with a system that is relying solely on purge, what you'll find is every single time you have a layer deposited of powder, you have a spike in oxygen content. So the majority of non-vacuum-based systems are going to operate between 500 and 1,000 parts per million. What this does is it really drives oxygen at the weld bed itself. So for highly reactive materials, titaniums, aluminums, these metals at elevated temperatures are sponges for oxygen. So if you start with a grade 23, kind of a metal grade titanium, you may have 5 to 6 uses depending on the surface area of what you're printing before you've now lost the chemical composition of your grade 23 powder and either have to dope it or you now have to kind of downgrade the powder. Same thing goes with other superalloys like your heavy nickel Inconels. As you're building these components with higher oxygen environments, you're going to end up reducing weldability and reducing fatigue strength. With a vacuum powder bed system, obviously that removes that as an issue. So I think really what we focus on for the DMP 320 is to use a vacuum system to remove the oxygen initially, allowing us to operate under 25 parts per million. What this does, and everybody will tell you, yes, our powder's recyclable. The majority of the industry, when they say they recycle powder, what they mean is they can remove larger particles and then get back to a particle distribution that can operate in the system. What they don't mean is that their powder is chemically the same or has not chemically changed. For any vacuum-based system, that is what we mean. We mean that we have not uptaken any oxygen in reactive or non-reactive metals, and that powder we've shown over years for same batches stays statistically identical to when it started, allowing you to not have to build an infrastructure of engineering around changing powders. So again, there's probably another 2 days with a seminar we can give on why does this matter and how is that going to affect your overall supply chain. But it's important to note that not all powder bed fusion systems are created equal here. There's a video on the bottom that will get running for the post edit here so that everyone can see. What you'll see is with the 320 system, using that vacuum, we've essentially developed a method to scrub humidity and oxygen out of our powder at the beginning of each build, allowing us to no longer have allowing us to not have to worry about the long-term chemistry of the powder. Again, we'll get this video. I definitely encourage everyone to reach back out. As you want to understand more about this, my team here in San Diego or the sales teams, we could certainly work with you and help you understand how industrializing this solution is going to impact both your engineering and manufacturing organizations. So back to lightweighting. Let's go to the next slide. Really what I want to spend the majority of time on here is why are we lightweighting, and then what components have really met muster that make sense from a cost standpoint, an overall total cost of ownership, and really have walked through intense qualifications either with FAA, NASA, or NTSB. So first, since my background is on the aerospace side, a very early key adopter of this technology has been the satellite industry. And so I've got a few pictures on the right I'll explain in a second, but really the reason the satellite industry is a prime adopter of this technology, especially in the powder bed fusion systems that are vacuum-based, is because they pay a tremendous amount of money to fly components. If you're flying your components at a geostationary orbit, you're somewhere in the $20,000 to $50,000 range per kilogram that you put to geostationary. Obviously, this is going to vary based on what you're flying, but as you can see, every single kilogram really in space counts a lot in the tens of thousands. So reducing that fuel use by lightweighting your component is really going to help you reduce the cost. And actually, what's kind of a more important note for those of you in the satellite industry, what we've found to date is that people don't actually reduce their overall launch bill. What they do is they use that weight reduction, and that's in our mass savings, to add more functionality to the satellite. And in most cases, it's batteries. They'll add lifetime. It allows them to provide additional value to their customers by not flying weight around that's not necessary. Next. So why else in the satellite industry are we doing this? You want to improve part performance, right? So the ability to stiffen. Yeah, there you go. The ability to stiffen your ribs and your construction components allows you to fly larger objects or add functionality to those parts. The ability to lightweight anything allows you to add more battery power or really to optimize flow paths. So we'll talk a little later about radio frequency components. Being able to optimize those components in a way that does not add cost really can improve the functionality of your satellites. Another major part of the satellite industry, why they're a very early adopter, is what they call the buy-to-fly ratio. And so obviously they use a lot of advanced materials for satellite production. Because those materials are very tight specifications, they'll end up having to buy very large billets, and then if for every 40 kilograms they purchase, oftentimes they only end up using 1 kilogram. So when we talk about lightweighting, we're not just talking about material reduction, we're actually talking about material overall use reduction. So for, this is kind of one of the compounding benefits of additive is that in traditional manufacturing, when you want to reduce weight, add complexity to a component, you're inherently and often exponentially adding cost. It's actually the opposite for additive manufacturing. As you increase complexity, increase part functionality, reduce weight, and increase surface area to volume ratio, you are functionally reducing cost by reducing metal. So in an additive system, it actually is really a beneficial cycle to say, as we focus on which components to use, let's add more complexity, not less, and that really helps with the cost justification, helps make it a functional part. To the next slide here. So let's really dig into what this example I've had on the right is. So this is something we've had for a while. It's a partnership we did with Thales Alenia, and it's for antenna brackets for geostationary communications satellites. If you look at the part on the right, obviously this is done with an inspired generative design. This is topological optimization, basically taking the primary components, the force bolt structures, applying which your worst case loads, and then iterating, in many cases tens of thousands of times digitally to find out where you actually need metal. Now, I want to caution you that anybody here that's used topology optimization equipment, whether it's Altair or anything else, what you'll find is that it really gives you a base structure for what needs to be printed, but it does not do all of the work for design for additive. Right, so what it does is it allows you to understand where you do need metal, and then what you need next as a next step is skilled design for additive engineers that understand how to combine what metal is necessary, combined with what is a structure you can print. Oftentimes, adding a little bit of metal, a few grams, even a few locations, allows for a self-supporting function that significantly reduces your overall cost. So in this case, we say it's an optimized bracket. It is, but it's optimized not just for strength and weight, but also for 3D printing. The end result here is we were able to reduce their production time by 50% and give them a 25% lighter piece. Now, there are 4 pieces per satellite bracket. These have been in orbit for nearly a year, and they have a long-term plan to continue to manufacture these. One critical component of this, and this is, I want to make sure everybody leaves kind of with this bit of knowledge, is that this component here was actually done on the design side in tandem with 3D systems, as well as early production, all done in this case in our Belgian facility in Movement. And so what we've done with Taoselania, and where we generally partner with large industry, is to help with the early design. We've got a wide array of material scientists and applications engineers here that help do the full functional design as well as early production in the effort to help ramp up the customer for in-house manufacturing. So kind of the model looks like this. You start interfacing with either my team or some other team of 3D systems. What we do is we help you identify the component, help you really target what's going to be best for additive, and then we begin to do early, low-rate initial production until it ramps up to a point that machine ownership makes sense for you. At that point, we're the manufacturer of the machine, material, and the component. We help you ramp up your internal production and then become your overflow manufacturing facility. So as you go through, you'll see a lot more of this kind of operation. The next slide. Here's a component that, again, I said, using a software like Altair is very beneficial for lightweighting. That's not the only key to lightweighting. In this case, we actually worked with Airbus Space and Defense to produce a radio frequency filter. So this is in this use case here, it's a Ka band filter, so very, very high frequency, which requires a significantly fine surface finish. If you look at the top right here, what we had to do is take traditional radio frequency waveguide design and really throw it away and start to go back to the fundamentals of design practice of radio frequency. And what we found is that the way RF waveguides and filters are designed today is actually quite difficult to manufacture an additive. But the way radio frequency likes to move and be filtered is kind of a very organic, self-sustained design that, in this case, reduce weight by 50% and improve passband rejection. So again, here's another component where it's a full design side redesign that allowed for a 50% weight reduction and has been in orbit since going on half a year now. Next slide. Let's see, we're running low on time here, so we're going to hit a few of these relatively quickly here. Again, you can always follow up. So this is work we're doing with the European Space Agency. It's a separated combustion wall chamber. And so what this does is it allows them to combine multiple combustion chamber functions, again, think through design, but also allows them to reduce overall density by 80%, because it turns out adding exterior structure and kind of a lattice, think of a truss-style system, is what they needed to both maintain the part rigidity itself, but also allows for better external cooling. So it allowed for a much more thin wall combustor and weld flange while combining multiple chambers. Next slide. You'll start to see a lot of this stuff when it comes to fluid flow and injectors. And so this is kind of another work we did on fuel injector design with the European Space Agency. Again, you take original design, and normally these things are designed with outer domes, allowing for better cooling to make sure that they understand the internal flow. Using an external lattice, we're able to get better thermal conductivity on the outside, and coincidentally, or actually really not coincidentally, it provided us a support structure that could be in situ built with the part. So again, we take a component that's traditionally manufactured, redesign it for its purpose, right? So as opposed to designing fluid flow passages for what angle you have to drill it, we design fluid flow passages for how fluid needs to flow. And that path alongside using a external lattice structure allows us to really get the best of both worlds while still cutting part weight. Next. So here's I'm going to call this one lightweighting 1.0, right? So in a lot of cases, you'll want to lightweight your component but really you've got a functional design already built in. And like I said, using the traditional today design straight out of the box and additive is rarely the right decision. In this case, what was done is we've taken a piston, what you've seen here is a piston head and an impeller. We've taken the internal components of those and replaced them with a lattice. So on the impeller section, obviously there's an area for a drain hole and there's an open space. What we've been able to do is reduce the target weight by nearly 1 kilogram. On the piston head, however, just to avoid post-operations and post-welding, we were still able to reduce part weight by some 20 to 30% by filling with lattice and then leaving that powdered infill. It's roughly about 70% of the density of the melted powder. Through a post-sintering process, leave the powder in, center it in place, and then, no more drainage, but still a reduced weight component. And so, again, I'd mentioned earlier that you would often want to drain the powder. In this case, it actually worked out to be a lighter weight component that was fully functional while leaving the powder in and centering it in place. Next. So here's another automotive application, and this one is really hits on every subject of lightweighting and optimization. Generally, for an intake manifold, it would take an aluminum casting, and as you're building through castings, you've got complex gating, minimum wall thicknesses, a lot of material that really is for the casting process, not for the final result process. So the original aluminum casting is really going to be limited, and so that you cannot add lattice structures or really go to super thin walls. But what you find is if you really are trying to optimize a structure like an intake manifold, one, aluminum is not the best metal for it. Really, titanium offers you a better strength to weight ratio. And then two, the optimized structure for this is really, it's not necessary to have thick casted walls. It's only necessary because of the casting operation. So transitioning to direct metal printing, we're able to, A, optimize the geometry. Now we don't have to worry about fluid flow of the casting itself. And B, really minimize that wall thickness down to what's necessary as opposed to what's necessary for castings. This allowed us to go down to even a 1/2 mil wall thickness using titanium and get an overall mass reduction of 50%. So this really hits it all. As you'll find when you're optimizing these structures, you need, especially if you started with aluminum and you're transitioning to a more advanced metal, you'll find that you need significantly less metal to meet your design size, and then a tremendous amount of what your engineering organizations are used to designing for is really designing for the process. So what we encourage people to do is to rethink that design for process and focus on designing for 3D printing for applications like this. Next. Wow, right on time, only a minute over. So let's talk about the future. First of all, there's no possible way anybody can predict the future. But we can talk really about where metal printing is heading right now. So obviously, if you were to Google 3D metal printing, you'd see dozens, if not more, of types of 3D metal printing, and there's more coming out every month. But obviously, the use of metal printing, both in the application technology and in the materials themselves, are advancing at a breakneck speed. There's trying to keep up with that is the growing sophistication of software, right? So as we really push into new advanced metals and new advanced lattice structures, software that previously was more than sufficient to analyze parts now is finding itself lacking in how do you analyze advanced lattice structures? How do you analyze non-isotropic material properties? So obviously the software world is going to have to move fast as it is to keep up just with the mechanical structures and applications printing. Combine that with the fact is now we're able to push closer to the envelope of ideal, a lot closer to what is are really the mechanical properties required to meet an application. What that's going to require is better print monitoring. And so you'll see companies working a lot more aggressively. There's a little bit out there now. A lot of this is more, it's traditionally called melt pool monitoring. What it really is kind of a thermal weld pool monitoring. But that technology is still very young and still has a long way to go. But as kind of the industry moves forward, I think you're going to see a lot more innovative functional ways to monitor. Only I'd caution you here is as you review in-process monitoring offerings, understand, really dig into what you're going to use that data for, because it will become critical, but I would definitely caution you that a lot of that data is good data to have, but with no known use case yet. And then last is increased research and innovation on part design, right? So I'd say the biggest development that is happening in the industry now is education, right? As people are learning that you can use additive for different functions and learning how to design for additive, seeing a big change in engineering organization, all the way from design functions being combined with the manufacturing functions, and then down to really instituting specific design for additive departments. This motion, this kind of gyration of the industry to develop those groups is critical. Just like when CNC was first rolled out, or when any new technology comes around, the way things are designed for, not without limitations, but it has different limitations, and then that's going to be a kind of a critical move as this technology grows. And that's it. That's not all I can talk about, but that's all I'm going to talk about today. So I'm happy to move on to questions, and I think we've got some good submissions coming in, and we'll start to answer some of those.
So, thank you, Brian. Wonderful presentation. We do have an awful lot of questions, and we don't have that much time. So I'm going to apologize to everybody that has been asking questions, that we won't be getting to a good number of them. But we will have somebody from 3D Systems contact you to discuss in detail about your queries. I also want to just introduce Greg Elfring. He's a VP of Sales for us, and he's going to be helping us on the Q&A. And he also has a good insight into the research being done, especially lightweighting metal parts for automotive. So we thought he would be a good addition to this. So there's a number of different questions, but in the main part, the first key one is Greg, if you could just give us an overview of what metal materials are available to print with, please.
We have a range of materials that we classify as laser form. This is a branded family of materials that 3D Systems offers that have kind of complete turnkey build styles that when utilized with the material and the build style can achieve specific mechanical properties. So we break them into two classes, reactive and non-reactive, or ferrous and non-ferrous. The materials that are ferrous are your iron, your nickel-based, so miraging steel, cobalt chrome, stainless steels, which are 316 and 17.4, and then we have, as I mentioned, nickel-based materials, Inconels, that complete a suite of non-reactive materials. The reactive materials, there's really two primary materials that we offer today. The first is multiple grades of titanium, from pure titanium to Ti-6.4 to Eli grade titanium, and then an alloy of aluminum that most closely matches a casting aluminum at this point. So again, if you use the 3D Systems laser form materials and the build styles that are optimized for the different machines, then you can achieve repeatable mechanical properties that are stated in our specs. So that's kind of a turnkey way of achieving desired properties without having to do too much work or research.
All right, thank you, Greg. Brian, I've got a question for you here. It's how about the process accuracy, that is? What are the dimensional tolerances obtainable by the metal AM process? Could you talk to that?
Sure. So unfortunately, this is never a popular answer, but the real answer here is it depends. What I can tell you is kind of a broad swath, is that it's really going to depend on overall part height and part location. And so just to kind of give you some general numbers, If you were to hand me a part that's, the full build height, 10 inches or more, what I would tell you is that as you go up on the part, you're going to start to lose repeatable positional accuracy. So if you hand me a drawing that says you need to be plus or minus 2 or 3 thousandths of an inch on location, what we'll recommend is post-machining that operation. And if you start to tell me that it's plus or minus 10 thou on position with a looser overall tolerance, say it's a whole dimension, then I think that's something that we will be able to repeatably hit time after time. Now, if these are all vertical-based holes that are tolerance not position, but really just hole size dimension, those are all, if you're at the plus or minus 3 thousandths, you're on a vertical position and you're closer to the bottom of the build, where the overall tensile stress or the built-in stress of the welding isn't going to move it, then obviously that plus or minus 3 becomes very doable. But again, as you see, think of this really fundamentally as you're welding. If you've got 10 inches and then you're doing 1/1000th of an inch, you've got 10,000 different layers of weldment. So as you grow that part and build it, we do a lot of work to hold it steady through stress relief. The reality is the taller you build this piece, the more it can functionally move around as a final finished part. And so keep that in mind. Part of what we can help, whoever who's asking here, is that we help folks review drawings, and then we can give recommendations based on those geometries of what we think we can hit.
All right. Thank you, Brian. Another question for you from one of our attendees. Are you working with any entity about certification of lattice parts for aircraft?
So certification of lattice parts for aircraft. So right now, the aircraft industry, I'm going to go ahead and speak strictly on the commercial side. Obviously, the defense side is often quite locked down and not open for discussion. So on the commercial side, the only really adoption of powder bed fusion has been on really at most secondary structural. And so I'd say the industry is really tiptoeing into that. Any lattice work that's being done in the commercial aviation industry is really non-structural, very similar to what you'll see in that ESA example that is really used for more heat distribution as opposed to any structural work. That's simply because obviously fatigue is a huge issue for aiming in the commercial aviation industry. And so as you assign fatigue to an object, you're going to start taking away lattice just because of its failure mode.
All right, I think we have time probably for one more question. And again, I apologize because we have so many questions that people have. I think just to talk a little bit about 3D Expert, a great question here. How do you decide between different lattice structures in other settings? Does 3D Expert offer any guidance or recommendations for which lattices to use? Brian, I think that's a good one for you as well.
Yeah, so it's really going to depend on what you want, right? So if your goal for designing a lattice structure is, so let's use a few examples here. So if you've designed a nice solid cylindrical support structure, and then you're worried about crushability, right? Using something like that's stochastic or really based on density infill lattice, something that's kind of internally random, is going to help provide good, we'll call it crushability resistance. Right? Now, if you want to use a lattice more for thermal transfer, then really your goal there is to start to manage a little more of the surface area to volume ratio, right? That's where that gyroidal lattice or some of those other structures come in. So to date, it's still going to be heavily focused on the engineer. What 3D Expert provides is the ability to adjust those. And then the ability to analyze their structural effect, or at least their basic structural effect on the build and use of the part itself. But I guess to answer your question, it's still really going to be heavily dependent on a good engineer understanding what the goal of that lattice is. Is it crushability, heat removal? Is it a simple infill for support structure? And that's really going to help guide what structure you want. And then using that FAA tool, you'll be able to know if it suits your needs or not.
All right, fantastic. We're a couple of minutes over on our schedule, so I think we're going to end here. but there is one question that I myself can answer, which is, yes, the webinar is recorded and will be available in a couple of days, and links will be set out. I understand some people had audio problems, and hopefully this will make it easier for everybody to properly hear what was said by Brian. So thank you, everybody. Thank you to the attendees for all of your questions. Thank you, Brian and Greg, for helping me out on this webinar. And everybody have a really good week. Thank you.
Thank you.
Thanks, everyone. Cheers.